In this video, I'm going to overview very briefly the mathematical language, notations, and conventions we will use in this course. You may already wonder if you have the adequate math preparation for this course. The math requirement of Ontario undergraduate geoscience programs varies a bit from university to university, but the minimum requirement is one course in calculus, A here. Normally, the requirement is 2 terms of math, and many students would take Calculus 1 and Calculus 2, A and B here. Some would take a combination of Calculus 1 and a linear algebra course, A and C here. Depending on the program and the school, sometimes all A, B, and C are required. If you have all A, B, and C, you are well prepared in math for this course. If you have any 2 of these 3 math courses, you should be fine. But anyhow, you should have at least A, Calculus 1. You will certainly find the math language a little bit challenging in this course if you only have Calculus 1. There is a great mathematics fitness textbook for science students that I enjoyed reading when I was a graduate student. And I highly recommend this textbook to you while you are taking this course. You are not required to have learned a mathematics application like MATLAB or MathCAD, but if you have, it is an asset. I will focus on notations and conventions in this brief overview because most of these are related to linear algebra. You will find that I go over linear algebra content quite a bit. So let us start with the concept of vectors. A vector is a quantity that has magnitude and direction. A vector is often represented by an oriented arrow. Changing the sign of a vector reverses its direction. Multiply a vector by a scalar changes its magnitude, changes its length. 2 vectors are equal only if they have equal magnitude and a parallel direction. Vectors are added by putting them in tail-to-head strings. The vector sum is a vector from the tail of the first vector in the string to the head of the last vector. The tail of the first vector and the head of the last vector. Remember, V, W, Z are not necessarily in the same plane. So this is a geometrical way of adding vectors. In order to handle vectors analytically, we use Cartesian coordinate systems. In a Cartesian coordinate system, a vector V has a projection on every coordinate axis. So the 3 projections are the vector's Cartesian components. Another way to look at the Cartesian components is to regard a vector as a linear combination of 3 orthogonal base unit vectors. We can regard V, a general vector, as a combination of 3 unit vectors, each parallel to a coordinate axis. E1, E2, E3 are unit vectors, parallel to x1, x2, and x3 respectively. So any vector can be represented as a linear combination, and the coefficients are Cartesian components. Of course, if we choose a different Cartesian system that is equivalent to a different set of base unit vectors, the Cartesian components will be different. Imagine that we have another coordinate system. It's a primed system, x1 prime, x2 prime, x3 prime. It's not shown here. Then the vector can be expressed in another primed set of unit vectors. We often write vector, the linear combination, in a shorthand way. We write them simply as VI-EI or VI prime, EI prime. This is the Einstein summation convention that we will use throughout this course. By this convention, an index that is repeated in a product means a summation over that index from 1 to n for an n-dimensional problem. Here it's a 3-dimensional problem, so VIEI stands for summation with respect to I over 1 to 3. The length of a vector is given by this relation, following the Pythagoras theorem. The quadratic length of a vector is represented by this. It's v1 squared plus v2 squared plus v3 squared. It can be written as this. Using Einstein's convention, it's vi. The index I is repeated. It means it's summed. Because the repeated index implies summation, it makes no difference whether it is an I or k that is repeated. A free index is an index that is not repeated in a product. That means a list of formulas or components. Therefore, Vi stands for V1, V2, V3. So I is a list of all the components. Often we do not need to write out the base vectors explicitly. We denote the vector V just by its components, Vi. Another notation that is used a lot is a shorthand for derivative with respect to a spatial coordinate. We write the derivative of A with respect to spatial coordinate xi as A, I. Therefore, ui, j stands for this. It's a derivative of ui with respect to xj. Now if we combine this shorthand with Einstein's summation convention, we have this. So ui, I stands for the summation of three derivatives, because I is repeated. Using Cartesian components, the operation of vectors become very simple. So the addition of two vectors is simply the addition of their respective Cartesian components. The dot product is defined by this. The dot product of two vectors is a scalar. In terms of Cartesian components, this dot product can be written very simply. So it's just this. It's ui, vi. I is repeated. Because I is repeated, it stands for summation over 1 to 3, because it's a three-dimensional vector. And using the dot product definition, the angle between two vectors can be calculated using this formula. The cross product of two vectors is a new vector. The length of the vector is u, v, sine theta. The direction of the vector is perpendicular to the plane formed by u and v, and the direction is toward the right-handed screw from u to v. In terms of Cartesian components, the cross product can be defined this way in terms of determinant. A matrix is a rectangular table of numbers or mathematical expressions, and these numbers and expressions are called elements of the matrix. The size of a matrix is specified by the number of rows and the number of columns of the matrix. So here it's a 3-row and a 3-column matrix. We say it's a 3 by 3 matrix. 1 row but 3 columns, 1 by 3 matrix. It's a 4 by 1 matrix here, etc. The element of a matrix can be numbers or can be mathematical expressions. We can define a matrix function in terms of variables. The Cartesian component of a vector can form a 3 by 1 column matrix. It can also be represented by a 1 by 3 row matrix. The element at row I and column j of a matrix is denoted by Aij. The transpose of a matrix is a new matrix denoted by A transpose T here. The ith row of the transposed matrix is the ith column of the untransposed matrix. So it has this relationship. In other words, the rows and columns are swapped when the matrix is transposed. If a matrix has the same rows and columns, we say it is a square matrix. For a square matrix, its trace is defined as the sum of the diagonal terms. Using Einstein's summation convention, it can be written this way. Another symbol that we will use a lot is called the Kronecker delta. It is defined as delta ij equals 1 if the indices are the same, I equal j. If I is not equal to j, it is 0. Note that there is an identity here. So delta ikvk always give delta I. This is like the change of index from k to I. The matrix I defined in terms of Kronecker delta is called an identity matrix. It is identity because A multiplying I equals I multiplying A and equals A itself. I is like the concept of 1 for numbers. Only square matrices have identity matrix. So non-square matrices do not have such thing as an identity matrix. Two matrices can multiply. The matrix multiplication AB makes sense only if the number of columns of matrix A is the same as the row number of matrix B, and it's defined this way. So A multiply B produces a new matrix. Its ij component is this. If A is a square matrix and another square matrix B exists such that A multiplying B equals B multiplying A and equals the identity matrix, then B is said to be the inverse of A, and it's denoted by this symbol. For a square matrix, it has a determinant, which is a scalar. For a 2 by 2 matrix, its determinant is defined simply by this relationship. For a 3 by 3 matrix, the determinant is defined this way. It's the product, red, subtract the green products. If A is a square matrix and X a column matrix, it's a vector, then A multiply X produces a new column matrix, Y. We can say that Y is a transformed version of X due to A. It is of special interest in continuum mechanics to find those special vectors which after the transformation by A remains parallel to the original vector. And we call those special vectors eigenvectors. So an eigenvector satisfies this equation. Its transformation by A produces a new vector that is parallel to the original vector, but with usually a different length. So lambda here is a scalar. It's called the eigenvalue associated with the eigenvector. Now we use tensors and matrix notations in this course, and I would like to clarify these two notations. So a second order tensor T expressed in terms of a set of base unit vectors EI, it's written this way. So the Tij are its Cartesian components associated with the base unit vector EI. Like with vectors, which are first order tensors, we rarely have to write out the base vectors explicitly. So we can denote the tensor just by its components, Tij, which is a matrix. We use matrix to present the Cartesian components of a tensor. Tensors can multiply, and the tensor multiplications include dot or inner product and tensorial product. We are going to use dot product only in this course. Dot product or inner product between tensors is called tensor contraction. They are single index contraction, double index contraction, and high number index contractions. Here are some examples of single index contraction. If A is a second order, N is first order, A dot N produces a first order tensor, and its Cartesian components are these. N dot A also produces a first order tensor. Its Cartesian coordinates are this. Note, A dot n is not the same as n dot a. The single index contraction between two second-order tensors A and B is this. They produce a new second-order tensor. The Cartesian components are AIK, BKJ. K is the dummy index. Double index contractions of tensors. If C is fourth order, it has 4 indices, and A is second order. C column A stands for this. It produces a second order tensor whose Cartesian components are this. If A is on the left side of C, double index contraction, it produces a second order tensor whose Cartesian components are this. Two second order tensors double contracting produces a scalar. Two fourth order tensors double index contraction produces a new fourth order tensor. Remember that repeated indices stand for summation with respect to those indices over the range of 1 to 3 because we're dealing with three-dimensional space. Note that single index contraction A dot n produces the same Cartesian components as the matrix multiplication of A and n. However, n dot a is not the same as matrix multiplication NA. In fact, if n is a column matrix, A a square matrix, n on the left of A makes no sense. There's no definition there. So, if the tensor product in the tensor contraction produces the same Cartesian components as a matrix multiplication, we will use matrix notation instead of the tensor notation. When no ambiguities occur and the operation makes sense, matrix notation will be used instead of tensor notation, and that is the notation we use in this course. High-order tensor contractions cannot be reduced to matrix operations immediately, therefore they will be written explicitly, either in terms of the tensor format or in terms of their components format. So it should always be understood that the Cartesian components of a vector, a second-order tensor or high-order tensors, are always associated with a specific unit-based vectors. The vector V has Cartesian components Vi. That Vi is specifically associated with EI. If we choose a different set of unit-based vectors, the Cartesian components of the vector will be different. The same is true with tensors. However, these Cartesian components follows the tensor transformation rule. Defining a matrix Q as the dot product of the primed unit-based vectors and the unprimed base vectors. With Qij, the Cartesian components of a vector transforms according to this. For second-order tensor, the Cartesian components transform from one set of unit vectors to another set of unit vectors according to this. For second-order tensors, Q occurs 2 times. For second-order tensors, the tensor transformation can also be written as a matrix multiplication. For high-order tensors, their Cartesian components transform across coordinate system in a similar way. Fourth-order tensor Q will occur 4 times. In all these expressions, repeated indices stand for summation over the range of 1 to 3. So tensors also can be inversed. For second-order tensor, if A dot B equal B dot A, and the result is a unit tensor, so it's a Kroneck delta Ij, then we say A and B are inverse of each other. B is the inverse of A. And this inversion can be carried out just with matrix inversion. Fourth-order tensors can be symmetric or may not be symmetric. Elastic and viscous stiffness tensors are symmetric. Ij can be swapped, KL can be swapped. So this is called the minor symmetry. They also have an additional symmetry that is called a major symmetry. Its ij and kl can be swapped. So ij kl equals kl ij. The Eshelby tensor we will encounter in this course, S, is also a fourth-order symmetric tensor. However, it only has the minor symmetry, but not the major symmetry in general. For fourth-order tensors having at least minor symmetry, its inversion is defined by the following relationship. So the double contraction of C and M equals to the double contraction of M and C. It produces a fourth-order symmetric identity tensor, JS, and JS is defined in terms of Kroneck delta. So JS IJKL component is defined by this. If C and M satisfy this, we say M and C are inverse of each other. All these operations will be handled in mathematics applications like MATLAB in this course. So it's important you understand the principles that are involved in the calculation, even though you are not doing the calculation by hand. That is my brief overview of mathematics. Thank you for your attention.